Let's take a look at the intrinsic masses of the hierarchy of quarks. And first, let's look at the heaviest of the quarks. The top are T quark. And we can see here that it will be composed of a generic D quark and a scalar boson plus. And the generic D quark will have an initial or assigned mass of 200 electron units. Now, here we have the combinatorial values for each particle system. Here are the generic quark, here are the scalar boson plus. If we look at the sum of these, we'll see that the sum of these is 3. Now, it will be the case that whenever the sum of a system composing quarks is not 1, that the scalar boson will carry a mass factor of 220 or 200 times the generic mass. And so let's look, in this case, we start with generic of 200. And in this particular case, the mass factor will be 200, but it will be times 2000 because the electromagnetic factor of boson plus converts the generic D into a generic U, into the generic D, which is now converts it into a generic U, which will carry a mass of 2,000 units, and that 2,000 units times 200 will give us 400,000 for the mass, 400,000 electron units for the mass of the top or T quark. Now, another thing to consider is that whenever we multiply the combinatorial values, we either have a positive times a positive, as we have in this case, and sometimes we'll have a negative times a negative, as we'll see in the leptons. Then other times we will have a positive or negative generic times a positive or negative scalar. And in each of these cases, either the scalar boson's mass factor will increase or decrease the mass on the generic quark. So whenever we have a positive times a positive or a negative times a negative, and so we get a positive result, then the mass will increase. But whenever we have a positive times a negative or a negative times a positive, we will see that the mass factor will decrease the mass carried by the system. So now, here we have a B or bottom quark. And we again have a generic D, which just gives us a mass of 200. And then we have a boson 0. This boson 0, though, is in a system that has a total combinatorial value of 3, not 1. So we'll see that we actually will have a mass factor of this boson 0 of 2. And so we get 2 times 200 gives us 400. And then here we have a boson 0 that actually is carrying a combinatorial value. In this case, that combinatorial value that it carries will be 20. And 20 times 400 will give us 8,000 electron units for the bottom quark. Continuing here, we have again a generic D quark. Now here we have another boson plus. So this boson plus, through an electromagnetic interaction, is going to convert our generic D into a generic U, and in combination with this boson plus, which is flavored, it will then be a charm quark, and that charm quark will have 2,000 electron units. And here we have another D quark, and in this case we have a boson 0 that is flavored, so this D quark will be a strange quark because of the flavored component, but it has a boson 0, and the total combinatorial value is 1, and since it's 1, then the boson 0 will not affect the mass on the generic D, and so for the strange quark, it will be 200 electron units. And so there we can see with this schema of assigning mass factors to the boson, scalar bosons of either 2, 20, or 200, depending on the combinatorial value, we have for the higher and middle generation masses for the quarks that is consistent with the standard model.